That's the Standard Model of particle physics, our best attempt to summarize the fundamental ingredients and recipes of everything around us. It's a remarkably successful theory, explaining a vast amount of what we observe in the quantum world. Yet it leaves us with more questions than answers. At its heart, the Standard Model describes the universe as a grand play of fundamental particles interacting through forces. These particles are the smallest constituents of matter, and their interactions govern everything from the formation of stars to the way light interacts with your eyes. The Standard Model doesn't just catalog particles, it predicts their properties and interactions with remarkable accuracy. However, some aspects of this elegant theory remain shrouded in mystery, particularly the question
Standard
of why
Model
particles
classifies
emit.
fundamental particles into two categories, fermions and bosons. Fermions are the building blocks of matter, while bosons carry forces mediating interactions between the fermions. Imagine fermions as the bricks of the universe and bosons as the mortar holding them together. Fermions are further divided into quarks and leptons. Quarks make up protons and neutrons, the constituents of atomic nuclei. Leptons include familiar particles like electrons, which orbit the nucleus, and their less familiar cousins, muons and taus, along with their corresponding neutrinos. Bosons are the messengers of the universe, carrying the fundamental forces. The photon, for example, is the boson responsible for the electromagnetic force, governing everything from light and electricity to magnetism. The strong force holding the nucleus together is mediated by gluons. Finally, the W and Z bosons mediate the weak force, responsible for radio accesses. The Standard Model has its share of puzzles. One of the most significant is the existence of 18 free parameters. These are numerical values within the model that cannot be predicted by the theory itself, and must be determined through experiments. These parameters are like dials that set the fundamental properties of the universe, dictating the masses of particles, the strengths of forces, and other crucial constants. The problem is that the values of these parameters seem arbitrary. There's no obvious reason why they are what they are, and even slight changes to these values could result in a vastly different universe. This fine-tuning problem has puzzled physicists for decades. Why are the parameters of our universe so precisely set to allow for the existence of stars, planets, and ultimately, life itself? Is it just a cosmic coincidence, or is there a deeper explanation lurking beyond our current? The enigma of mass. Why particles weigh differently? One of the most fundamental questions the Standard Model grapples with is why particles have mass at all. Intuitively, we think of mass as an inherent property of matter, but in the quantum world it's not so straightforward. The Higgs boson, discovered in 2012, plays a crucial role in explaining the origin of mass. According to the theory, the universe is permeated by a field called the Higgs field. Particles interact with this field to varying degrees, and it's this interaction that gives them their mass. Imagine the Higgs field as a kind of cosmic molasses. Some particles, like photons, pass through it effortlessly, experiencing no resistance and therefore remaining massless. Others, like quarks and electrons, interact strongly with the field, acquiring mass in the process. However, the Standard Model doesn't explain why different particles interact with the Higgs field with different strengths, resulting in the vast range of masses we observe. Why is the top quark, for example, hundreds of thousands of times heavier than the electron? The answer likely lies beyond the current framework of generations of matter, 3 copies, 1 universe. Another curious aspect of the Standard Model is the existence of 3 generations of matter particles. Each generation is a heavier, less stable copy of the one before it. The first generation includes the familiar up and down quarks, the electron, and the electron neutrino. These particles make up the vast majority of ordinary matter we observe in the universe. The second and third generations contain heavier versions of these particles, such as the charm and strange quarks, the muon and muon neutrino, and the top and bottom quarks, the tau and tau neutrino. While the heavier generations play a role in high-energy processes, they are unstable and decay rapidly into their lighter counterparts. Why are there 3 generations when only one seems necessary to build our universe? This redundancy remains an unsolved. Beyond the Standard Model, the quest continues. Despite its remarkable successes, the Standard Model is not the final word in particle physics. It leaves many questions unanswered, urging physicists to search for a more fundamental theory. The search for a theory of everything that can explain the universe's deepest mysteries, from the nature of dark matter and dark energy, to the unification of all forces, is one of the most profound scientific quests of our time. Several promising avenues of research are being explored, including string theory, supersymmetry, and loop quantum gravity. These theories attempt to extend the Standard Model, offering potential solutions to its shortcomings and pushing the boundaries of our understanding of the universe. The quest for a deeper understanding of the universe is a journey into the unknown. Every new discovery, every theoretical breakthrough brings us closer to unraveling the secrets of the cosmos. The Standard Model, with its puzzles and mysteries, serves as a stepping stone, guiding us towards a more complete and elegant description of the universe and our place within it.